All right, welcome back. Kicking off our second class here. So I'm going to touch on a few things. This class will be a little different than the other one. In the other class, we did a broad, sweeping overview and touched on a lot of different topics. There was a lot of content in that class. In this class, we're looking to dive really deep. So it's kind of the opposite of that. We're not going to touch on such a wide breadth of topics, but the topics that we do touch on, we're going to focus on getting to know those really well. So I'm interested to hear your feedback in this. At the end of the course, some of you might like this better, some of you might like this less, depending on your preference, but it's going to be maybe a slightly more methodical approach to it, a slightly slower pace, but the expectation we're looking for here in the content is a deeper level of understanding. This is a reminder for me to do attendance, but I'll do that in one of our breakout sessions so I don't forget that. I want to get moving here so we don't run out of time. What we're going to talk about today is we're going to do an introduction and overview, just go through our course syllabus, which looks just slightly different from the other one. And then one change, I'm going to make a couple of changes. One change I'm going to make is on Sundays. From 9 to 10 a.m., I'm going to have office hours. So I will share a link every Sunday at 9 a.m. And if I'm busy for some reason, I'll let you guys know what day I shift this to. But I'll share a link every Sunday, a Zoom link every Sunday at 9 a.m. And if you just want to pop in, you can pop in. You can ask questions. I'm happy to work through homework problems or whatever is of interest to you. You can bring your work problems there and we can sit and discuss them. We don't really have enough time in class, or we didn't last semester to do that type of stuff. So looking to offer you guys that opportunity if that time works well for everybody. And then we're going to start to dive into overview of model evaluation. What is that? And then we get to our first break here. For the second part of this, we're just going to take a step back and review some mathematical notation. Nothing too deep here. We're just going to review what functions are, what that notation looks like, what a summation is, because you will see that a lot in calculations of performance metrics for machine learning models. So it's important just to remember exactly how those work. And we're going to touch on, again, predicted versus actual. Again, this is stuff that you've heard before, but we're taking a little bit of a deeper look at them. So this course almost might feel like somewhat of a review in terms of the material, but you should have a greater understanding of the concepts here. We're going to touch on true positive, false positive, true negative, false negatives. And then finally, in the end here, we're going to get to some of the heart of the content. And we're going to start building our strong foundations here. Accuracy, precision, and recall, and really understanding what each of those are. We have a couple of breakout sessions in here as well. Okay, let's dive in. Again, I'll have the course schedule here at the bottom, and we'll cross these off as we go through each one. So let's start by looking at the syllabus. So the first thing I want to share with you guys, another change I implemented here is maybe a little more organization to our course material, which will probably make you very happy. I tried to put everything in one location here. I shared this Drive link with you guys. So go ahead and check that out whenever you'd like. I'm going to post each session as a folder in here. You should have access to it. And then I'll put the assignments in here, the breakout sessions. So one place to look, all of the materials, so you don't have to try to jump around on my GitHub, ever-changing GitHub repo. So we're going to click on the course syllabus here. Oh, let me change my, there we go. So in our course syllabus here, there's description, prerequisites. It really doesn't change too much from the other course. You guys are all really familiar with the machine learning concepts and programming in Python, looking for just a little bit of familiarity with mathematical notation, but we're going to cover what you will need today. So If you're not feeling comfortable with the things that we talk about today, I would review those, make sure you feel good, because that's the language that we will use to describe the other metrics. And here's some objectives, things that you'll be able to do by the end of the course. I have no book for this, but I do think this textbook, which is, again, publicly available. I don't even think there's a physical book. This is just an online textbook. This one's really, really good for understanding metrics in a really friendly and approachable way. Here is our class schedule. You'll notice I made a typo in here, so I need to shrink these down. I accidentally have session 3 in here twice, but there are 2 different topics. So you may have noticed in my course schedule that actually ended up in 9 classes and not 8. So I will revise this. I have to think about this when I'm going to shrink or pull out of that. So there will only be 8, but just be aware before we get to section 3, I'll have that revised there. Typo on my part. But we're going to start with introduction and overview, and then really dive into accuracy, precision, and recall today. Next, on Wednesday, we're going to talk about F1 score, which we've touched on a little bit in the past, but we're going to really look at that in more detail. Confusion matrices, log loss. We're going to understand probabilistic models, basically thresholds, which we've talked about again in the past, but looking at implementing those and understanding those more. Precision recall curves, what is model calibration, why is it important? Then we're going to look at the regression metrics. So we've touched on some of these: mean absolute error, mean squared error, R squared, all the derivations. But we're also going to look at how do we predict error plots for those in the same way that we do for and in the same way we predict those types of error plots for classification models. Then we're going to look at some advanced classification metrics, such as categorical cross-entropy. And then we're going to evaluate the models for robustness and sensitivity, touching on k-fold cross-validation again. So if that was something that that you felt like you need a little more time with, we will come back to it. Ensemble model evaluation and more refresher on the ethical considerations and maybe a deeper dive there as we have like a deeper understanding. So this class is different in that the weighting is more on the exam. So again, less tactical implementations of actual algorithms and more a conceptual understanding of how these metrics work, how to measure them, how to use them, and what their values are. We do have 2 assignments, so you'll have more time to do your assignments. Those will be spread out evenly over the class, but we have no project or anything along those lines. So everything will be focused more on the exam. Again, just pass or fail class, so 70 above, 69 below. So your actual grade does not matter. I just give you a grade so that I have a balanced way of calculating that. Knowing that there's a stronger emphasis on the exam, I will be providing, if we go to class 1 introduction, you'll find all the material here. I will be providing learning objectives for each class. So when we go into this presentation, you'll see that there are a lot of slides. There are 58 slides in here. That's probably typical. And so out of all that material, what do you really need to focus on? And that's what the learning objectives are going to be. And so in this one, the overview of model evaluation, this mathematical notation. So in this case, these are the mathematical notations you're going to need to learn, but really for this class, it's a focus on these metrics. So accuracy, precision, and recall. So hopefully this will help you focus on what topics are important for takeaways for that. Okay, that'll be in each folder. So I think now, let's see. Any questions on that before we dive in?
Love the structure. It's
Oh, great.
fantastic. And thank you for providing some office hours for us.
Absolutely. Awesome. Let's dive in. All right, model eval and metrics. Oh, this is just our schedule. So what we're going to talk about here is we're going to go through we already went through the course syllabus here. We're going to touch on an overview of the model eval. Then we're going to dive into mathematical notation here, and then some introduction to those first performance metrics, accuracy, precision, and recall, which we're going to continue to build on Wednesday. So if there's a focus, I would say definitely understand those. Okay, so overview of model evaluation. What is model evaluation? You all probably already know this, very familiar with this from the last class, but it's the process of assessing what is the performance of our model. How well is it doing? And why should we do this? Because it helps us understand how well the model generalizes to unseen data and whether it meets our objectives that we're trying to accomplish. It can allow us to compare different models. That's the key term there is if we did model evaluation, but we only ever had one model, we don't have a baseline to really compare it to for you should select this or this. Model evaluation really allows us to say, hey, we have all these different models trained over all these different metrics. Which one is the best for our task? All right, that was my 10-second overview. So that part went fast. But review of mathematical notation, which is seems intense, but once we get into it, you'll see that you're probably already very familiar with it. So why is mathematical notation important to machine learning and data science and these evaluation metrics? It helps us represent these concepts in really precise and concise ways. So we can, you can easily look at something, a mathematical formula, and understand exactly what that is doing. And it's generally applicable to a lot of different data sets. And so this notation will help you navigate a bunch of different metrics. So we're just going to build a baseline understanding of the various metrics for you to start with, to explore. But as you look into other metrics, understanding this notation can really help you grasp those. So the first one is functions, which again, we probably touched on in the last course, but we just said, hey, this is a function, and then we kind of like moved on and did other things. Now we're going to dive in a little deep and take a moment to think about what is a function. This is a bit of a refresher again, but we have a f of x is usually how this is referred. So that's our function name. Our function is f. This could be g, it could be h, it could be z. This is our function name, and the input that we are providing to it is x, and then this is what we expect to output. So this is our function is equal to our output. So for example, if we put 0 in here, if 0 was our input, f at 0, that's how you would say that, f at 0 is equal to, well, now 0 takes the place of x, and this is 0 squared. So it's 0. So f at 0 is equal to 0. F at 1, if we put 1 in here, is equal to 1 squared, which is 1. So f at 1 is equal to 1. So this is a function. The definition of a function in the context of machine learning is that it represents a mapping of input data from x to an output value or to a prediction. In supervised learning, f of x is often referred to as the predictive model or our hypothesis function, and it takes a series of input features as its argument, and it produces a prediction or estimate based on those features. So if we remember back to our linear function, our y equals mx plus b, we have, which maybe I talk about in a second, but we have our y equals mx plus b. So our f of x equals 2x minus 2. And this is the same thing I talked about before, is if we want to find f at 5. What is f at 5? We put -5 in here. 2 times -5 is -2. So that's -10 minus 2. F at -5 is equal to -12. Can anybody quickly do in their head what is f at 5?
Eight.
F at 5 is 8. So f at 5, 2 times 5 now takes the value of x, that's 10. 10 minus 2, that's 8. So coming back to linear functions, review from our last class, if we're thinking about simple linear regression, our y equals mx plus b, otherwise known as, instead of putting y, we could put f of x. F of x is equal to y, so they're interchangeable. F of x is equal to mx plus b, or y equals mx plus b. Remember, this is our dependent variable, our slope here, independent variable, and our y-intercept. Oh, that picture is so grainy. I'll find a better one. But this is the same thing that we just said. We have f of x equals mx plus b. What if our function is f of x equals 2x plus 1? Well, we talked about in this other example just putting 1 or 2 values. We tried -5 and we tried +5. But what if we iterated through every value that we had in our input set, or every value that existed? We started at -infinity, and then we went to 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and went to positive infinity. Well, you would get a line if you did that. If you put every single value, 2 times 1, 2 times 3, 2 times 4, and that is what this line would represent here. So here's some other examples of functions. Basically, all of the algorithms that we talked about are a function. So in linear regression, f of x represents a linear relationship between the input features x and the target variable y. So remember, we started with y equals mx plus b, and then we generalized to f of x equals beta sub naught plus beta sub 1 times x sub 1 plus beta sub 2 times x sub 2, all the way up to beta sub n times x sub n, where these betas are the coefficients or parameters of the model. So this is the function, the more extended, generalized functional form for linear regression. And we can do the same thing with logistic regression. So f of x is equal to 1 over 1 plus e to the negative beta transpose x. You don't need to memorize that for this class, but that's just saying that this is another function. So this is the function, the functional form for logistic regression. Neural networks and decision trees can have functions as well. So an example of a function that we're going to use in this class, which we talked about in the other one, but just as a refresher here, is the summation function. So taking you guys back to, I don't know when the first time this occurs in the math courses, maybe algebra. Taking you back to algebra, this is a summation functions that says that the variable, down here we have the variable that assumes the value from m to n. So this is the initial index. I have to cough, sorry. 1 second. So this is, where are we going to start? What's the index we want to start to? Do we want to go from 1 to 10, or do we want to go from 7 to 10 or 8 to 10? What's the position that we want to start at? So this is the initial index. I is just a variable. I is a variable. It'll always say I here. That just tells us what I is at each iteration. I takes on the value of m. First m is 0, and then m is 1, and then m is 2, and then m is 3. N is the final index. So this is, where do we stop? Do we stop at 10? Do we stop at infinity. And then this is the actual summation term. This is what we're going to do the operation to. So if we look at this, so next slide after this. So let's look at a definition for this. The summation function, and it's often denoted with this symbol here. It's an operation that represents the addition of a sequence of terms. And it's used to add up a series of numbers or values according to some pattern or rule. So where A is the pattern and rule. This might be another way that you'll see it. Again, I equals our starting index, our ending index, and then A at I means A at 1, A at 2, A at 3, what value our I takes on at that point in time. So this is what it'll actually look like. Those were the general forms. Here's an actual implementation. So sum over 4 times n, starting at 1, you say n or I, where n equals 1, all the way up to 6. So this would be 4 times 1 plus 4 times 2 plus 4 times 3 plus 4 times 4 plus 4 times 5 plus 4 times 6. So you go all the way up to 6. I have to think if it's inclusive of 6 or not. I can double check on that. Oh, here, this example will tell me. It is inclusive. Okay, inclusive of your starting point and your ending point. So here's the summation operating as a function. So now we're putting these two concepts together. The concept of that summation, which is a function, and what we talked about as a function. So summation going from 1 to 4, starting point 1, all the way up to 4, f of n, where if we wanted to calculate that, we would write it this concisely, but we know in our head, or what the calculation is under the hood, is it's saying the function at 1, the function given 1. So given 1, if we give 1 to this function, in this case, we're doing 1 plus 1. I don't have the actual f of n on here. I'm realizing I should. But function at 1 plus the function at 2 plus the function at 3 plus the function at 4. And we stop at 4 because that's our stopping point. Now we evaluate. What is f of 1? Well, if we pass 1 to this function, it's 1 plus 1. If we pass 2 to this function, it's 2 plus 1. If we pass 3 to this function, it's 3 plus 1. If we pass 4, so then we get the results of these, which is 2, 3, 4, and 5. Then we'd add them all up, and that would be 14. Any questions on summation functions?
It's not assume that it's plus, right? Or it is.
Oh, good point. Yes, this will always be adding up whatever this function is. This will execute and then add whatever that execution is to the next element in the series. So you would pass 1 to it, it would execute doing its 1 plus 1, and then that would be 2. But yes, to your point, you're always adding them. Okay. All right. Any other questions on summation? I think this is it for our summation and functions. Okay. Predicted versus actual. We talked about, we used this quite a bit in the previous class. We're going to use this a lot in this class. This is the whole point of evaluation metrics, to be able to compare what did you predict to what are the actual ground truth values. So the notation of predicted versus actual values are used a lot in evaluating the performance of machine learning models, and they represent the model's predictions compared to the ground truth of those actual values from the data set. So why hat? Usually you will not have this spelled out separately. I need to figure out how to put math notation in PowerPoint slides, but it's the Y with the little caret on top of it. I put it next to it here, but imagine it's on top. So it's usually called Y hat. these are our predicted values, and they represent the outputs or the estimations made by our models given a set of input features. So f of x is equal to y hat. Y hat is our output, our predicted output given the input to those. In regression, for example, the predicted values are continuous or numerical outputs. Remember, we talked about the difference between regression and classification problems. And in classification problems, y hat values can be class labels or probabilities assigned to those different classes. Our actual data or our ground truth, this is our y. These are actual values, often denoted with y, and they represent the ground truth for our values in our data set. These are what are used to train our model. And in regression, I mean, these are going to be pretty much the same as I said on the other slide, because y and y hat are going to be of the same data type. But in regression problems, they're numerical outcomes for the model that the model aims to predict. And in classification problems, they're class labels. So here's y hat. There we are. Here is y hat, where our predicted values are. When we say y hat, it's typically representing a vector of values or a list of values. So we say this is y hat. It can represent one instance. We can say this is what we predicted the price of a house would be. But typically, when we're using it in the context of these evaluation metrics, we're thinking about all of the predictions that the model made on the validation set, or all of the predictions the model made on the test set. So when we say y hat, it's usually a series of predictions. So what is y? Y at index 1, at position 1, means what is the prediction that the model made for the first row, for the first record in the data set that we gave it in the test set. What is the prediction that the model made for the second record in the data set? All the way up to the nth record in the data set. Nth meaning if you have 100 records in your data set, up to the 100th record in the data set. Actual values, again, represented as a vector. Whenever we say y with no hat on it, we're typically, unless we're just kind of being loose with our terminology, if you're looking at this in like an algorithm, in a actual evaluation metric, the y is going to represent, again, a vector of values exactly the same way that y hat does. But these two are going to correspond to each other, meaning what the true value is for one, if this was really an apple, then we can look at y hat. Well, did we predict apple or did we predict banana? So these values correspond to each other positionally, meaning y at 2 is the actual value for the y hat at 2 prediction. Okay, any questions on this notation? We're going to use this a lot. So y predicted versus actual, it allows us to assess the performance of the model and evaluate it against these metrics: precision, recall, many other terms. And it, again, helps us understand how well the model generalizes. That's how we'll actually use it, is how it generalizes, or how it captures these patterns, or really how we can select which model has the best performance. Another terminology thing that we're going to talk about constantly throughout this class, at least in terms of classification metrics, if we're talking about a classification problem, is positive instances. So in the context of ML, a positive instance is an instance where the data point belongs to the category of interest. So if we're predicting fraud, one would be it was fraud. So that's the standard. Usually if you have a data set and it's about fraud and you have 0 and 1 labels, you don't usually label your fraud instances as 0. Usually 1 means that thing has occurred. So that's what a positive instance, a 1, in terms of our data set usually means that has occurred. If you're training a breast cancer classification model, 1 usually means the individual has breast cancer. And knowing the terms positive and negative is important because this is how we're going to define accuracy, precision, and recall. Negative instances is exactly the opposite of that. So it's all the instances where the class, the category of interest, what we're looking for did not occur. So we're trying to predict bananas. Everything that's not a banana would be a 0 or a negative instance in a binary 1-0 classification model. So this picture represents that. We have these labels for our model for, let's say, binary classification, which just means binary 0 or 1. There's only 2 classes. It is a banana. It isn't a banana. You may hear any of these terms. Positive, true, 1. It was spam. Or I guess let's use spam instead of a banana. We're trying to predict if it's spam or not spam. The spam class is either the positive target, the true target, 1. I'm gonna avoid using the word true because that's confusing with the ground truth and like the actual predictions versus the actual predictions. But you'll hear me say negative or 0 for ones that are not spam. Okay, so a couple of ways that these are used. I might have already mentioned these, so we will see. But in binary classification, there's typically 2 classes, a positive class denoted with 1, like I said, and a negative class often denoted with 0. Positive ones belong to our area of interest. And for example, a medical diagnosis task where the goal is to predict whether someone has a disease. I said breast cancer, diabetes, any disease. Positive instances are the individuals who have the disease. We can also look at multi-class classification where we're trying to predict more than 2 classes. So in that case, we don't have 0, 1. We have multiple instances for each class. So each problem will have its own positive instances. So for example, in the handwritten digit task where we had numbers from 0 to 9, and we were trying to predict, is this a 0? Is this a 1? Is this a 2? Instances for the digit 3 are images of the digit 3 are positive, while instances for the digit 7 are images of the digit 7. So each one has its own positive and negative instances. So if we have a image that is truly 3 and you predict 3 for it, that is a positive instance. If you have an image that is truly 3, but you predict 7 for it, I said that backwards. If you have an image that is anything else that is not 3, those are your negative instances in regards to looking at the 3. So this is, we'll talk about this more in our cross entropy metric, I think in class 3. Imbalanced data. So there's situations, you guys are familiar with class imbalance, where some representations are more prevalent than others. And positive instances may be relatively rare compared to negative instances, specifically fraud. Fraud is usually less than 1% of the data set. So this handling requires careful consideration and care. There's methods that we explored for addressing class imbalance data, such as SMOTE, oversampling, undersampling techniques. Okay, now we're going to get into some terminology. So we know what positives are. We know what negatives are. Now we're going to get into true positives, false positives, true negatives, false negatives. And we're going to use these. Now we're getting to the heart of the meat of the topic today. We're going to use these to really build on what is accuracy, what is precision, and what is recall. And I'm going to do a time check here, 6:50. I think I might do our break now. I had it planned for the first 50 minutes. This will be a good spot to stop. I know it's early because we just got started, but we're going to pause now or our breaks won't be well separated. So let's do a 5-minute or 10-minute break. Let's come back at, sorry, trying to find a clock on here. Oh, it's 6:50, right?
Mm-hmm.
Let's come back at 7. All right, kicking us back off here. Okay, diving into, we're much ahead of schedule here though, by the way. So I'm talking really fast today, apparently. That's unusual for me to go fast. Usually I'm way behind. So good, we'll have some time for breakouts today. True positives. So we really want to work to understand these next four concepts. True positives, sorry, switch back to my presentation. Here we go. True positives, false positives, true negatives, and false negatives. When we look at true positives, these represent the instances that are correctly classified belonging to the positive class. So if we are predicting fraud, these are the instances for which we predicted it was fraud. Our y hat predicted fraud, and our y was actually fraud. Our y hat was 1. Our y hat was fraud. So that is a true positive. We predicted positive, and it was actually positive. So in this case, the actual class and the predicted class are both positive. For example, test of a disease, true positives are the patients who have the disease and we were correctly identified as having the disease by the model. Okay. I'm gonna jump back and forth between this picture I have here, I've decided. So if we look at the true positives, that is this section here. We predicted it was positive and the prediction was actually positive. Okay, false positives, to have something to contradict that, are situations where we incorrectly classified that it was belonging to the positive class. When in fact, they belong to the negative class. So we said, yes, this person is fraud, or yes, this person has breast cancer. Yes, I think this person has diabetes. Our y hat was 1. But in reality, when we look at the ground truth, when we look at our y vector, our ground truth data, it was actually 0. It actually belonged to the negative class. So these were situations where the model predicted a positive outcome, predicted a 1, but the actual outcome was negative in reality. It was 0. We were wrong in that we predicted 1. See if I got all that. Yes. Okay. So let's look at our slide again. Here, we just talked about false positives. That is this dimension here. To put it more succinctly, we predicted positive, it was actually negative. True negatives, or TN, these represent. So now we just looked at all the situations for which a positive prediction could occur. So we looked at when you predict something as positive, when you predict 1, it's either true, the ground truth, in binary classification. The ground truth is either 1 or it's 0. So it's either a true positive or it's a false positive. Now we're going to look at our negative instances. What are the situations where the model predicted 0? And again, in a similar fashion, it can either be a true negative or it can be a false negative. So a true negative is a situation where we predicted that it was a 0, predicted that it was a negative, and in reality, when we looked at the ground truth, when we looked at our test set, when we looked at y, we found that it actually was 0. So both what we predicted, when we predicted 0, it was actually 0 as well. So for example, I guess the example I put in here is in a binary classification task to detect spam emails. The true negatives are the emails that we correctly said, this is not spam, and in reality, it turned out it was not spam. Our false negatives are the situations where we predicted something was 0, predicted it was negative, predicted it was not spam, predicted it was not breast cancer, predicted it was not a banana, but in fact, it did belong to the positive class. It was spam, it was breast cancer, it was a banana. So our model was wrong in the way that it predicted 0. So it was a false negative. We predicted a negative outcome, but the actual outcome was positive. And the example I put in here is a medical test for a disease, so breast cancer or any test that you're running. The model incorrectly identifies that the individual does not have the disease, when in fact they do have the disease. That is a false negative. This is a simplified chart of all that, which I find useful. So true negative, predicted negative, actually negative. Predicted is exactly equal to our y hat. Actual is exactly equal to our y. So y hat was negative, y was also negative. That's a true negative. This is a true positive. These blue boxes are the 2 situations in which the model was correct. This is what the model got right. The gray boxes are where the model was wrong. It's either wrong in the way that it predicted the positive value, or it's wrong in the way that it predicted the negative value. Again, all of this is for binary classification, where we either have 1 or 0. We only have 2 situations that we're handling. It is the simplest place to start. Later, we'll get into multi-class classification. So here's a visual way of looking at that. That's kind of fun because it's funny. But a true negative would be, we predicted this was not a hot dog, and in fact, it is not a hot dog. It's a pizza. And a true positive is, we predicted this was a hot dog, and in fact, it is a hot dog. A false positive is, we predicted this was a hot dog, but in fact, it's a picture of a dog wearing a hot dog costume, which is not a hot dog. And a false negative is, we predicted this is not a hot dog because it doesn't really look like a hot dog, but actually it's a chili dog, and that's a hot dog. So if we need a way to kind of grasp these, this can kind of conceptually help settle that in. So let's try it out. This will be our first breakout exercise. I want you guys to try to calculate the true positives for the following scenario. We have a binary classification model, and here are our predicted values. The first array here is our y hat, and the second array here is our y. So given this data, can we calculate what are our true positives, what are our false positives, how many, sorry, that's what I'm looking for, a count, and how many true negatives do we have, and how many false negatives do we have? Take maybe 10 minutes, think about this. You toggle, I dropped the link for the slides, you can toggle back through the slides, or if you want me to jump around, let me know. Okay, I'll let you guys work on that for a minute. Oh, sorry, I'm just gonna 10 minutes, so 7:20. All right. How are you guys feeling? Are we able to give a stab at that? Does anybody want to?
Well, in its most simplistic form, it's 50-50 given this model.
50-50 for which of these?
Oh, I mean, for the accuracy.
Oh, 50-50. Awesome. You already calculated accuracy. Absolutely. I'm going to have you guys do that next. I have a notebook for that. What did you get for true positives?
2.
2. So because we have this situation here where we predicted 1 and it was actually 1. And we have this situation here where we predicted 1 and it was actually 1. There's no other situations where we predicted 1 and it was actually 1. What about false positives? 1 false positive. This is where we predicted 1, but it was not actually 1. It was 0. And then true negatives. 1 true negative. This is where we predicted 0, but it was actually 1. And then false negative.
True negative?
True negative. Sorry, did I misspeak there? True negative.
Wouldn't we predict 0 and the true value be 0 for true negative?
Oh, yes, I'm so sorry. Autopilot here. Predicted 0. The true value was 0. Sorry if I said something else. True negative. Predicted 0. It was actually 0. And then how many false negatives?
2.
2. We predicted 0. It was actually 1. We predicted 0. It was actually 1. All right. Feeling good about that. We're going to have a strong foundation. So in summary, these are the things that we talked about. These are the things you should feel very comfortable with. Our y at I just meaning the index, meaning the row or the observation that we have that actual label for our ground truth for. Our y hat, our predicted value, f of x is our function that maps x to output. Here's our summation function representing the sum of the series from, in this case, I equals 1 to n. TP, FP, TN, FN, that's our true positive, false positive, true negatives, false negatives. I'll probably just most of the time use this type of notation, TP, FP, TN, FN, because it's easier, it's more concise. Where P represents our positive instances and F represents our negative instances. All right. Finally, the first content for today, introduction to performance metrics for classification problems. So that everything we just talked about concludes our summary, our review of stuff that we probably already know, but just touching on again. So now let's talk about performance metrics. And the first one, as I don't know who it was alluded to, is accuracy. This is a very fundamental evaluation metric because it is so commonly used in the world today, not just in machine learning, but in general. You hear everybody say, what accuracy do you have with this? Or what was the accuracy of that? A lot of times people will say, what was the accuracy of the model? When they don't always exactly mean accuracy. So you'll notice that I'm very careful with my wording. I almost always use the word performance instead of accuracy. And I would impress that upon you to do as well, because accuracy is an actual metric. It has an actual formula that we'll talk about. So it really represents a precise way of calculating a performance of something. So if we want to talk about generally how well the model did, I try to abstract using the word performance. Here was the performance of the model across these metrics such as accuracy or precision or recall. So what is accuracy? It measures the proportion of correctly classified instances, both positive and negative instances, in the total number of instances. So in other words, It's how often the model makes a correct prediction. So accuracy, it measures the proportion of correctly classified instances out of all instances, out of all predictions made. Diving just a little deeper, and here's where our notation comes in. The way we actually calculate accuracy is in our numerator here, we have true positives plus true negatives. These are the number of correct predictions. When we say, was the prediction correct? When we predicted it was positive, was it truly positive? When we predicted it was negative, was it truly negative? Those are the only correct predictions when we talk about TPFP, TNFN, true positives or true negatives. On the denominator, on the bottom side of this division line, we add everything up. So all of the 4 instances that we just talked about, true positives, the true negatives, the false positives, the false negatives. So I can't remember who it was, but when you said 50-50, you were adding the true positives plus the true negatives. So in this case, our true positives were, you might have to remind me, I don't have it up right now.
I think it's 2.
Our true positives were 2, and our true negatives, that was 1, thank you. So we have, jumping back to this slide, next one, that would be 2 plus 1, which is 3. And then we're going to add everything up. So we had 2, and we had 1, and we had 1, and we had 2. So that's 6, right? So we add everything up, 2 plus 1 plus 1 plus 2. If you want to sanity check this, it should be the length of your predicted values. So the length of this, and we can count that this is 6. So it should always equal each other. If we made a prediction on everything, which in this case we did. So in that case, it would be 3 over 6, which is how you get the 50%, 0.5, which then we convert to 50%. So this is how we would, how accuracy actually works under the hood, which I think is intuitive to all of you, which makes it a really good place to start, because we're going to continue to use the true positive, the false positives, the true negatives to talk about other metrics that we might use. And we're going to build to F1 score on Wednesday. Today we're just starting with accuracy, precision, and recall, but these are all foundational to F1 score. So let's talk about an example. Another example here for accuracy. Suppose we have a binary classification problem, and we want to predict whether the emails are spam, or a positive class labeled 1, or not spam, negative class labeled 0. And we have a data set with 100 email samples, and our model makes predictions for each email. Let's say the model correctly classifies 85 emails, either spam or not spam. So out of the 85 correctly classified emails, 50 are correctly classified as spam, true positives, and 35 are correctly classified as not spam, true negatives. What is the accuracy for this? I'll leave this here for just a minute so you guys can think, and then on the next slide I have the answer. I might have put the answer on here in the way I worded the problem, but we'll see. I did. I will change that next time. So I said 85 correctly classified emails, so maybe I kind of gave that away. But so the number of our correct prediction is 50 plus 35, which equals 85. So the accuracy is the number of correct predictions over the total number of predictions. We correctly classified 85 of them divided by 100. And then sometimes metrics are reported in percentages. So as you all know, we can just times that by 100, and then that's how we get a percentage. When you get it out of a model, it'll typically look like this. Sometimes when you're communicating to your stakeholders, they are more familiar with percentages. So you just multiply your model performance by 100 to convert it to a percentage. We had an 85% accuracy.
Is it always gonna be assumed that they are, 100% accuracy? Is it just assumed that they will say, so 85%, they're always gonna assume 100? Like, I don't know if
That's a good point. In this case, we had 85 out of 100, but this could be 85 out of, maybe we had 300 examples, or maybe we got 160 out of 300. But either way, that would give you some decimal point here.
right.
And then we would multiply that by 100.
Right.
So it is always 100 you're multiplying
Yeah.
by for the
Just
percentages.
when you're talking to stakeholders, because like earlier you said that 50 was 50-50, I think it was 10%. But like to us, if we're the second we said it's 50%. To us, that means like fail. Or I was thinking of grades, like 70% at least is passing, 800 that's not passing. So that's the same idea behind.
That's a good point. How we interpret what the percentage means or what that performance means is going to be very different based on your problem. So if I have a model, what we're going to want to do in that situation is determine what a baseline is, because our goal here is just to predict something and be correct at predicting this. So if you're thinking about like grades, I might want to predict what somebody's grade is going to be, but so the performance would be more along how good am I at predicting what their grade is going to be at the beginning of the year.
Thank you.
So some trade-offs, some things to be aware of for accuracy. First of all, it's a super simple calculation. How many correct? What's the entire population of things that you were trying to predict on? Really simple. It's very intuitive. People strongly relate to it. So if I say the accuracy of a model was, 92%, like that resonates with stakeholders. If I say the log loss was 0.1, it's hard for people to wrap their head around what that exactly means. So it's very intuitive and it's comprehensive. And what I mean by that is it's looking at the entire population. Some of these other ones that we're going to look at do not. But there are a lot of things to be aware of with accuracy, and it's used very carefully when assessing models, because it performs specifically very poorly on class imbalance data. So you would never want to apply accuracy to a fraud model. And that is because accuracy looks at the entire wealth of things. So if we have a highly imbalanced data set, let's say 1% of the data set is fraud and the other 99% is not fraud. So let's go back to our 1 and 0 labels. 1% of the data is fraud and the other 99% of the data is not fraud. If we trained a model that just predicted 0 for everything, it never predicted a single value for fraud. In terms of accuracy, our accuracy would be 99%. So to a stakeholder, that sounds really good. Your model can predict fraud technically with an accuracy of 99%. But in reality, we didn't actually predict a single instance of fraud. And that's not at all useful to the business. So in terms of creating a model to find fraud. So you should be really careful when using accuracy to represent class imbalance problems, because it may not represent the performance that you're looking for. There are intensive misclassification costs. So if you get something wrong, it has a really strong penalty for that because of that denominator. And compared to some other metrics, it's unable to capture the prediction confidence. It just says, how well did we do? It's not necessarily considering the probabilities underneath the hood. You know, it's not looking at the predicted probability for all of our predictions. So for example, if again, we have our fraud model, but we weren't really confident certain things were fraud, and we just predicted 0.51 for everything, that's a very different model from predicting 0.99 for everything. Our model has different levels of confidence. But when we look at thresholds, because we round everything above 0.5 to a 1, which we'll talk about more, then the way that's represented in accuracy, it doesn't capture that difference between a probability of 0.51 and a probability of 0.99. They're both just 1, and they're treated equally. So that's what I mean when I say it doesn't have an ability to capture prediction confidence. Any questions on accuracy? All right, let's talk about maybe a metric that you're not as intimately familiar with as accuracy, and that is precision. And precision measures the proportion of true positives among all positive predictions. So what are the instances in which we predicted it was fraud, it was actually fraud, and then on the denominator, what are the instances we predicted it was fraud and actually fraud, and the predictions where we predicted it was fraud, but it was not actually fraud. So it's all the situations where the model predicted 1. Out of all those situations, how many of them were actually 1? We don't care about anything we predicted 0. We're taking that, setting it aside for this metric. We're not even looking at them. Of everything we classified as a banana, how many of them were actually bananas? Or this is typically really important and used a lot in medical diagnoses. Because if we tell somebody that they have cancer, we want to know, of all those people we told that they have cancer, how many of them actually had cancer? So we're not looking at the people who we told didn't have cancer, but actually had cancer, which is not a good situation either, but we're not looking at this in that metric. Just who had cancer, and of everybody we told that had cancer, on the denominator or on the numerator, how many of them had cancer? Okay. So here's the definition for precision. It's an evaluation metric used to assess the quality of positive predictions for a classification model. And it measures the correctly predicted positive instances are true positives to all the instances that the model predicted were positive, regardless of whether they were actually positive or negative in the ground truth set. So why is this relevant? And I probably jumped ahead of myself and already said this, but it focuses on the accuracy of the positive predictions, which is particularly important in the scenarios where the cost of a false positive is very high, where it's really serious if you predict something is a positive, but it's not actually a positive. So medical diagnoses, we're predicting the proportion of the correctly identified patients with a specific condition out of all the patients predicted to have that condition. So this is, we're very concerned with getting things correct. When we do say that, that something is a positive class, this is a measure of how serious we are, or how good the model is saying is at actually identifying that. So interpretation here, the model makes a few false positive predictions, and it's selectively, a high precision. If it's a high precision, if value is closer to 1, then that model makes very few false positive predictions in selectively identifying positive instances. And that makes sense if we look at our formula here, because we have true positives both here and here. So if we had 100 instances and 99 of those were true positives, this would be 99 over 99 plus 1, which is going to be a 99% precision. If we had a lot of false positives in there, such as 50 false positives, this would be 50 true positives over 50 true positives plus 50 false positives. So it would be lower. It would be further away from 1, closer to 0, which would be a lower precision value. So a lower precision suggests that the model is incorrectly labeling negative instances as positive, and it leads to a higher risk of false positives. So here's a concept check, a question for you guys. I didn't know how to phrase this. Maybe when we look at TP, FP, TN, FN, which of those are not considered in the precision metric?
True negative.
True negative and false negative. Yep, you're right, Brendan.
Okay.
You're right. It was one of them. There were 2.
All right.
True negatives and false negatives. So we're not looking at any of the negative instances. Okay, let's look at another example. We're doing a lot of spam emails today. Binary classification is spam. We talked about that. I won't go through that again. 100 email samples. So we just pick 100 sometimes because it's easy. Yep, exactly. But out of 100 samples, our model predicts that 50 emails are spam. Out of these 50 predicted spam emails, so we have 50 instances predicted 1. We predict 50 instances of spam. Out of those 50, 40 of the emails are correctly classified as spam, and 10 emails are incorrectly classified as spam. 10 emails are incorrectly classified as spam when they're not actually spam. What is the precision? I'll give you guys a minute.
80%.
Yep, you're fast. All right, so we calculate this with the true positives over the, and I should have put brackets here because order of operations would technically say that you would divide true positives by true positives first. So sorry, there should be parentheses here. But precision is true positives. Over on the denominator, we have true positives plus false positives. So that's 40 over 40 plus 10, which is 40 over 50, which is 80%. So the precision of our model is 0.8, or again, if we multiply by 100, that's 80%, which means that out of all the emails that we did predict as spam, this is how you would interpret that or communicate it to your stakeholders. Out of everything that we predicted was spam, 88% of them were actually spam. So our model is correctly identifying spam emails 80% of the time among all emails predicted as spam. All right, that's precision. Now we're going to move on to recall. We have a time check. We're doing good here. Yeah, we're doing good. Okay. Okay, going to move on to recall here, which is, sorry, I messed my screens up when I did that. Here we are. Move on to recall, which measures the proportion of true positive instances that are correctly identified. So contrasting precision, recall looks at true positives Again, it's the same numerator that we had for precision, true positives. Here is precision, true positives, where precision was true on the denominator was true positives and false positives. But in recall, our denominator is true positives and false negatives. So this is out of all of the instances which we could have identified, out of all of the opportunities in the entire data set that we had to predict a 1 that were actually 1s, how many did we correctly predict as 1? So that's recall, and you can think of this as like you're trying to recall everything. You're recalling from your memory, right? Where all of these exist out there, how many of them did you actually recall? Okay, I don't know if I described that well, but here's a definition that maybe makes it a little more concrete. So, it's also known as sensitivity or true positive rate. By the way, you'll probably see it referred to as sensitivity quite a bit when people talk about how sensitive your model is. That's talking about recall. It is the same thing. It's an evaluation metric, and it's used to assess the completeness of positive predictions. So contrasted with precision, in precision, we were looking at how precise or how correct our positive predictions were. In contrast to that, we're looking how complete they were. So did we miss ones that were positive that we should have predicted as positive, but we predicted as 0? That's what this is asking. So I probably even have an example on I'll give an example. So in the example of the medical situation in the breast cancer or diabetes example, out of everybody who had cancer, and everybody who actually in our ground truth set had cancer, how many of those did we predict had cancer? Were there people that we said didn't have cancer, we predicted 0 for, and we sent them home, and then 10, 20 months later, we found out they actually had cancer, which is a bad situation. So this measures the proportion of correctly predicted positive instances out of all of the actual positive instances in the data set. So the denominator is all potential positive instances, all true positives plus all false negatives. So the relevancy of recall, it's focused on the ability of the model to capture all positive instances, minimizing the number of false negative predictions. And it's really important in situations where the cost of missing a positive instance is high, such as medical diagnostics. It's precision and recall are both important in medical diagnostics, where failing to detect a disease can have severe consequences. So sometimes you'll say, hey, we're going to err on the side of caution here, and we're going to maybe have our model predict more instances are positive than they actually are to increase our recall, to make sure that we try to capture as many of the positive instances as we possibly can. I gave an example for this, I believe, which is a situation where we're trying to predict who needed to take action on a document based on comments made on it. Was it legal? Was it compliance? Was it contract? Was it HR? There were 9 teams, 9 potential teams that could interact with this document. And they preferred that we notify a team, even if that team actually didn't need to take action on it, because the risk of not notifying that team and having that team not notified to take action on that comment was higher than the downside of having people over notified and then they go in and say, oh, I don't actually need to do anything. That was lower to them. So we cared less about precision and we cared more about recall. We wanted to have strong recall. If legal needed to take action on these documents, of all 100 documents, we wanted to have as close to 100 as possible, even if we predicted 150. So here's the interpretation for the metric. If you have like a recall value that's closer to 1 versus closer to 0, a high recall value, meaning closer to 1, indicates that the model is effective at identifying positive instances. It minimizes the number of false negatives. Conversely, a low recall suggests that the model misses a lot of positive instances and it leads to a higher number of false negatives. All right, in our example here, let's consider binary classification, and we're predicting patients who have a disease and patients who do not have a disease, 1 and 0, positive, negative. We have a data set with 100 patients, and we make predictions for each patient. Out of 100 patients, 60 patients actually have the disease, and our model correctly identifies 45 of them as positive. So out of 60 patients who actually have the disease, our model correctly identifies 45 of them as positive, true positives. However, our model misses 15 patients who have the disease, incorrectly classifying them as negative, false negatives. What is the recall?
$75%.
75%. So to calculate the recall, I got the parentheses on this time. Our recall is the true positives over the true positives plus the false negatives. So that's 45 over 45 plus 15, which is 45 over 60, which is 0.75. So the recall of our model is 0.75 or 75%, which means that out of all of the patients who actually have the disease in real life, our model correctly found 75% of them. So we found 75% of the positive instances that existed within the data set. Okay, so here is just a visual cue. Some people learn well from text. Some people learn well from pictures. Some people learn well from videos. So here's more of a visual cue if you're a visual learner. Sorry, it's a little brainy. That describes the difference between precision and recall. So in this picture on the left, this is all of our data. This is our entire, my mouse was on the wrong screen, sorry. This is all of our data. This is our entire data set. And here in the circle are the predictions made by our model that predicted 1. And everything outside of this circle, the model predicted as 0. So if we look inside of this circle, the things in this green area, we predicted as 1, and they were actually 1. The things in this red circle, inside the circle, but in the red area, we predicted as 1, but they were actually 0. So you see the zeros here. Outside of the circle, on the left side here, these are outside of the circle here in the slightly darker gray area. These are false negatives. So these are situations where they're actually 1, but we predicted 0, because remember, outside of the circle, everything we predicted is 0. And then on the right side here, these are true negatives. So we predicted 0, and they were actually 0. So one way you might think about precision is how many selected items are relevant. So we're going to take the green slice, and we're going to divide it by the whole circle. So the green slice divided by the green slice plus the red slice. we are not looking outside the circle. We are not looking at things that we predicted 0. We're only looking at things that we predicted as 1, our selected elements in this case. When we look at recall, it's a different part of the problem. We want to know how many relevant items are selected. So it is the inner circle green slice over this entire half of the picture, the dark gray area plus the half of the green slice. So it's saying of all of the potential positives that exist in the world of our data set, out of all the potential positives, how many did we actually capture? And that is recall.
Say that one more time.
Yep. Which one? Precision, recall, or both?
Just do both.
Both. Okay. So precision is looking at this half slice here of the true positives in the numerator. And it is saying out of everything on the denominator, it's saying out of everything that we predicted as 1, how many of those were actually 1? Out of everything that we predicted had cancer, how many people actually had cancer? What recall is saying is on the denominator, out of all of the potential instances in which we could have predicted 1, out of all of the ground truth values that are 1, how many did we predict as 1? You're welcome. Here's an extra resource. You'll find that all of those visuals I pulled on those formulas were actually pulled from this resource here. So feel free to, I'll even open this up and show you. Check this out. I find it useful. So you will see that I pulled those from here. So they dive into a little more detailed example, and it's spam, not spam, and they have visual aids here that show the labels in the data set. So it might be interesting if, and they actually show the correct prediction, all predictions, and they kind of have a visual way of like showing ones that aren't included. And so check this out. We're going to talk about confusion matrices next week. We're building to that, so there might be a little content we haven't touched on here, but it's a good description. Okay. You know, I forgot to do our breakout section for mathematical notation, so we're going to combine. Sorry about that. We're going to combine both of our breakout sessions together. So if you guys go to, and let's see, let's do one breakout session. Let's talk about it. Then let's take a break. And then let's do the other breakout session. And then let's talk about it. Okay, that's the plan. So if you go to this drive folder here, you'll see these notebooks. Let's start with the summation function. If you want to download that, put it in your location, your repository, wherever you're working from. It's also on my repo if you guys are interested in grabbing it from there, but I was trying to co-locate everything. This is, well, you don't have to jump around 10 locations. So I will open it on here as well. So we can, there we go. Back over. So here is the breakout exercise. What I did here, and I have to just remember, implement the summation. Oh, example discussed in class. So sorry, I should have paused earlier to do this. I need to make myself a reminder slide. Okay, here was the summation example that we talked about. where, I mean, you can do either of these. You can do this one, you can do this one. This one we don't have a function for, though. You can, it's n plus 1, we can assume from this, but let's do this one. We're from n equals 1 to 6, 4 times n. So here I have written a summation function that takes in a start, an end, and a term function. And I made a term function that was I to the power of 2. And we took, I ran this summation function and got the results here. So I called the function, I said, do I to the power of 2. I passed this term function, starting at 1 and going up to 5, ending at 5. For the breakout session, what I'd like you to try is to create your own term function for 4 times n, and try to implement that for n starting at 1 all the way up to 6. Let's spend 10 minutes doing that. 12 minutes doing that. Let's come back at 7:10. Were you guys able to do this? Does anybody want to share or talk about what they implemented here?
So I just added a couple lines actually to what you already had.
Excellent. What did you
Here, I'll throw it in the chat.
do? Yeah, perfect. Which chat? Hold on.
I'll do it in the class, the StreamYard.
Oh, StreamYard. Perfect. Let me. Oh, show. I think I have to show. I don't know how to do that.
Okay.
How do I see the chat? Oh, there we are. Sorry. I figured it out. Perfect. So let's try this. We're gonna. All right, we created a function here called term function 2 that takes in a value my_val, and it returns 4 times my_val. And so we're going to, our result is going to be equal to summation. We're calling summation function. We're starting at 1, and we're passing 6, and then we're calling term function. And then we're going to print it. I have to run my cells, sorry. Here we are, the result is 84. Is that what you guys got as well?
Yes, but mine didn't look like that.
Ooh, what did yours look like?
I basically just copy and pasted what you had and I just updated the return I times 4.
Right here?
No, the one on that one. Yeah, that's all I did. That's all I fixed.
We can do that as well. Return I times 4. We're going to rerun this. Oh, somehow we got. Oh, 6. Sorry.
Yeah.
There we are. And we have 84.
I did that the same way as she did.
Excellent. It's a beautiful thing about programming. Multiple ways to get the same very valid answer. Awesome. Any questions on this? Let's jump to the next breakout activity. Let's actually take a, if you guys haven't had a chance yet, let's at least do a 5-minute break. Let's come back at 8:22. I want to give you, if you guys have been just working away at working on that one, I want to give you a chance to step away. But if you want to look at our next breakout activity, if you haven't opened that up yet, it's going to be accuracy. And so you can check out this code. We'll come back at 8:22 here. And then we'll talk about this. All right, sorry about that. Accuracy, last breakout activity here, and then we'll be done for today. So accuracy and true positive, false positive, true negative, false negative. So we define a function here called calculate confusion matrix. Don't worry too much about what that is. We'll talk about that next time. But all it's doing is it's calculating true positive, false positive, true negative, and false negative given y true and y pred. And remember, y pred, that's our y hat. Y true is our y. So in this function, originally we create these variables, TP, FP, TN, FN, and we set them to 0. We're resetting it every time we call this function. And we say for true pred in zip y true pred. All that means is it puts together those pairs for each instance of a prediction, a true value, and a prediction in here. Now we have, I'll show you what it will look like. Hold on, I'll just type this out above. So if y true, for example, equals, I meant to put an equal sign there, equals 1, 0, 1, 1, 0, and y pred is equal to 0, 1, 1, 0, 0, then when we call this zip function, zip is basically creates a set of tuples so that now our list sort of looks like this, where the first tuple is going to be its true pred, so it's going to be 1, 0, oh, sorry, I can't look and type at the same time, apparently. 1, 0, so it's 1, 0, and then the second one is going to be 0, 1, 0, 1, and our next tuple is going to be 1, 1, and our next tuple is going to be 1, 0, and our final tuple is going to be 0, 0. Okay? So 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0. So that's the zip function. It takes two lists, and like a zipper on your jacket, if you have two lists, it zips them together. So now we have pairs in that indexed order. So that's what true is. True is this, pred is this. So as we go through this loop, what it'll say is if true is equal to 1, so if true is equal to 1, which it is in this case, and pred is equal to 1, well, pred's 0, so pred is not equal to 1, so we go to the LF. Now it says if true is equal to 0, true is equal to 1, so we go to the next LF. If true is equal to 0, true is equal to 1, so we go to the next LF. If true is equal to 1, true is equal to 1, and pred is equal to 0, pred is equal to 0, fn plus equals 1. So our fn was 0 originally when we made this. After one pass through with this first one, fn is equal to 1. So that says false negative has a count of 1. And this is a false negative because we said that it was, we predicted that it was 0, but in truth, it was 1. Sorry, I actually prefer to look at these with y pred on top. That's just a me thing. There we are. It's a true negative, or I'm sorry, it's a false negative. We predicted 0, but in reality, it's 1.
Is that more of a best practice, like pred? What I use for pred is the predictive numbers be more like we just set being read first, then true.
You know, I don't think it's a best practice. I put it there because I want to know what was predicted, and then I want to look at reality, but that's just a personal quirk. So then we have true positive down here, which are ones that we predicted as positive, and they were actually positive. We have false positives, ones that were again, if it was me, I would have, I should probably swap these in this programming here. But I like to think of the prediction first, but that's just a me thing. Ones that we predicted were 1, but in reality were 0. And then we have true negatives, ones that we predicted were 0. In reality, they were actually 0. And then we have our false negatives, ones that were predicted as 0, and then in reality were actually 0. So that's how we get our, that's our function we made, and here we're going to use it. So I'll delete this now, just not to confuse us with multiple vectors here. I think in mine I swapped this, so this was on top. So we have our predictions and our true labels, and then we can run this. And if you notice, this is the example from class. So you can validate your 2, 1, 1, 2 here in your calculation. And so I asked you guys to, or I'm asking you guys to implement an accuracy function. So make a function called accuracy and take in these values, the true positives, false positives, true negative, false negatives, and return and do something with them. You have to do something here, you know? Do something here to calculate accuracy, and then return an accuracy score. And we know from our discussion in class that this should be 50%. So go ahead and work on that. Spend maybe 10 minutes on that. 8:43, we'll come back, we'll talk about it, and then you guys can go a little early today. We flew. All right, let's talk about it. How did you guys implement your accuracy function?
The total samples added together, and I divided that by, or I divided the correctly classified by the total samples.
Classified, and then you call the accuracy score equals correctly classified divided by total, something like that.
Yes, ma'am.
And which ones were the correctly classified ones?
TP and TN.
TP and TN. All right.
No, TP and TN.
Oh, sorry about that. TN. TP and TP, that would be an interesting accuracy score. Okay, so let's call this. Let's see what we can. All right, 50%. Excellent. Did anybody else do this a different way, or any other thoughts or discussion on this?
Mine was pretty much the same.
Excellent.
So my question is more around, would you really do something like this with a really large set of data in the hundreds of thousands or more rows?
I think so, but I wouldn't make my own metric. We're making this metric because we want to understand how it works and how it's implemented. But I would use sklearn accuracy score. Hundreds of thousands of rows. It'll still run just fine. This is the same thing. We can even run it on our same data set. We'll get the same results here. But so let's try that. And then I'll describe why you would want to do this instead of creating your own. We can get rid of these. We have our own ypred, ytrue up above. And let's run accuracy score. So don't worry about that. Here we are. 0.5. So you're gonna get the same value. However, in sklearn, in addition to having some other parameters, you can do some normalization or some sample weighting, some more sophisticated things. It's extensible. If we look at the source code for this, what you will find, all this is just documentation. What you'll find is the way that they choose to calculate this is very computationally efficient. There are people on the internet who have too much free time on their hands and try to figure out ways they time computer code. They create like a start clock and an end clock, and they'll run sections of code, and they'll time it and see how fast it runs. And they'll get the code that runs as quickly as possible. A lot of this compiles down to a more efficient programming language than just Python. So that was a wordy answer, but sklearn accuracy score. I would use this, and it should run fairly fast.
Thank you.
Yeah, absolutely. Excellent question, though. Yeah, don't implement your own metrics. We're going to do it so we understand it, but this is a much better package for all those things. Great. Any other questions? Wonderful. We'll let you all go just a few minutes early. Thank you, guys. We'll see you on Wednesday.
Thank you.
Great, thank you.
I have a question.
Yeah.
So, I found,
Hold on one second. There we go. Waiting for people to stop dropping. Okay, what was your question?
so I had found this one, and let me see this. I will send it in the Slack, the picture. Okay, so I was looking at that picture to help me write the code for the accuracy thing, but I didn't know how to apply what we had to that so that I could get the accuracy score down
I
at
think
the bottom.
that we can do it exactly like that. Let's make another function here. Let's call it compute accuracy. And I see. So in yours, you're taking in y true, y pred.
Uh-huh.
So let's do it this way. Let me think. I mean, we can, there's a couple of options. Here's what just so everybody else can see, here's what this function is doing. It's saying correctly predicted 0, true label, predicted in zip, y true, red, if true, false equals predicted. Accuracy score correctly predicted over the length true. Let's see, score. And it should return the same thing. But instead, we would need to pass it by true y pred, and then still going to return 50%. If in this situation, we're skipping over calculating the exact true positives, true negatives, false negatives, and that's okay. For accuracy, we can just go through and say if the true label is equal to predicted, then it's a correct one. Otherwise, we don't care, and we'll just take the length of y true, or this should maybe technically be the length of y pred. But the length of all the predictions, out of all the predictions we made, how many of them were correctly predicted as we're counting here? So we can definitely do it this way. This is still a correct way to do it. What we're not doing is taking in true positives, true negatives, false negatives. If you're going to do it that way, calculate this method of taking them all in exactly like this is going to be a little more expensive to precision recall. So we can very easily transform this to be a precision and recall formula, whereas this one's going to be, we just have to kind of rewrite this to calculate precision and recall. Both are correct.
Okay, because I was struggling on the part, I didn't know what to do where it said correctly predicted, because in my mind, I was like, well, it correctly predicted 2, so would I put 2?
Here or up here?
Where it says correctly predicted equals 0. That's where I was getting stuck.
Oh, I see. The correctly predicted equals 0. This is just creating a variable for us to use so that, and it's resetting it to its original state. So when you're going to calculate the accuracy on a new metric, on a new data set, it's resetting it to 0 so that it's not keeping its old value that you calculated from before.
Okay.
It's more like a reset button here.
The sklearn thing that it had, oh shoot, what was it called? I'm trying to now. You had a code that was normalized equals false. And I'm looking at, I have looked a couple, I was like, what does it mean? So it returns, I didn't really understand, it returns as true or, I was trying to read that. If normalize equals true, return the fraction of going down, let's go down, so or just returns. Not up.
Clear?
I was trying to understand, because on the bottom it had,
Yeah, you as well.
this right here, yeah, like what, so I did that, but I'm just curious, what does the normalize equals false would, I was trying to look at everywhere
Good
else.
question. So normalize is one of the parameters that you can pass to the function. It can either be true or false, and the default is set to true.
Right.
So if you don't pass this parameter, it's by default true. And it says if false, it returns the number of correctly classified samples. Otherwise, it returns the fraction. So let's test that out here. For example, down here. Normalize equals false. We're going to get 3 because there were 3 out of 6 correctly classified samples. Normalizing it is normalizing it to all of the data in the data set. So if you put false, it just gives you the numerator.
Okay.
So how many samples were correctly classified? Was it 3? Was it 10?
3 out of the 6.
Was it
or whatever.
3,000? It's just 3 for normalize equals false. But if normalize equals true, it's going to normalize that to your data set, which makes sense, makes sense for that to be the default, because if you classified 3 correctly, it makes a difference whether you have 6 examples or 100 examples, what percentage were correct. So normalize equals true makes it a percentage. Normalize equals false makes it a count.
Okay. All right. Okay.
Good question. Any other questions? We have time.
I'm just trying to figure out how to understand this. I'm just trying to make sure. I think it's just throwing me off, like, you're saying 3 samples of what we used as our example are because I'm just trying to understand where the 3 is coming from.
3,
Or
let's see, here. So 3 were correct. We predicted 1 and it was 1. We predicted 1 and it was 1. We predicted 0 and it was 0.
Thank you. That's where, so 3 out of
3
those,
incorrect.
out of the
We
two
predicted,
bowls.
there's 6 of them total.
Right.
So if we put this as false though, it just returns 3.
Right.
It just tells you how many
Out of those.
you got correct.
Gotcha.
But if it's true, it divides by how many were in the entire data set. So it divides by 6.
Thank you. Thank you for that.
Awesome. Good.
You could print, if you wanted to see it, right, you could print Y true and Y pred. And it would show you what, 3 and 3?
Right.
Oh, no. No, I was thinking if you, it doesn't show you the increment, right? So if you do Y true normalized equals true. Oh, you have to do accuracy score. Okay, that's what I'm thinking out loud, right? You have normalized as true, but if you did it normalized false, I'd want to see the Y true and then the Y pred, right?
But these are just vector data types, so they're not going to change if we change the parameter to the function.
Yeah, I was trying to see if I could see 3 and 6, right? So if you get what I'm saying.
Oh, do you mean change the values here?
No, like so that I could, if I wanted to calculate the percentage, I would see 3 out of 6, right?
Oh, you want to know the total, the 6.
Yeah, so I was just trying to think through a way to do that.
The 6 will...
I'll play with that.
Good question. You could do it by 3 is what percent. You could do it. This formula is the 3 is equal to the total times the performance. So we could figure it out by, if we move things around in that formula, we could say that the total is equal to 3 over total. Total is equal to performance divided by 3, right? So I think we could do 0.5 divided by 3. Does that give us 6? No. I'd have to think about that too. There's something along those lines you can do.
Yeah, I was just brainstorming out loud. Thank you, though.
Yeah, absolutely.
It's good to
Great.
see the variations in everyone's work to compare.
I thought that went well. We're going to have more breakout sessions like this, getting everybody to share and interact.
Yeah, I definitely am seeing that there's more than one way to skin a cat, so to speak.
Absolutely. That's so useful because it's true in programming. There's many, many ways to solve it.
All right. Well, thanks. Appreciate your
Thank you,
time.
guys. Have a good one. I'm going to end the stream here.
Have a good
Cheers.
night.